Hello everyone, in this video, the group 4 members will talk about Fermi Dirac distribution function. Enjoy!
Hello, my name is Methulan Chispansing and I'll be presenting about the Fermi Dirac distribution function. What is it? It's also known as the Fermi function. It provides probability of occupancy of energy levels by fermion, which are kind of like electrons, and at 0 Kelvin, the energy level, the Fermi level, is at maximum. Here we have the Fermi function, which is Fe equals to 1 over 1 plus exponent E minus Ef over kT, where E is the energy in thermal equilibrium, Ef is the Fermi energy level, K is the Boltzmann constant in joules per Kelvin or EV per Kelvin, and T is the temperature in Kelvin. So what can we do with this function? Well, for one, we can plot a graph to see what the probability of the transition is. So at high temperatures, the transition is more erratic compared to lower temperatures. And that is all for me. Thank you.
Moving on, in order to understand the Fermi Dirac distribution function, we will need to look into some examples. We consider a specific system with equal distance between energy levels, ranging from 0.5 increasing by 1. Since electrons are indistinguishable from each other, only two with opposite spin can occupy a given energy level. The system contains 20 electrons and the minimum energy of this system corresponds to the situation. All 20 electrons occupy the 10 lowest energy levels without placing more than 2 in any given level, where it occurs at temperature of 0 Kelvin and total energy equals to 100 electron volt. You can see the example in this figure here. Then we apply basic postulate of statistical thermodynamics, assuming all possible configurations are equally likely to occur. The best fit was obtained using Fermi energy of 9.99 electron volt and kT of 1.447 electron volt. We can see the example more clearly with this figure here. That's all from me. Thank you.
Hello, now I will explain about impurity distribution function. Impurity distribution function is different from the Fermi Dirac distribution function, even though the particles involved are still fermion. The difference is due to the fact that an ionized donor energy level still contains one electron with either spin. The distribution function for donor. The donor energy level cannot be empty, and this will leave a doubly positive charge atom. The distribution function for donor is given below. The distribution function for acceptor. Also, because of the different possible ways to occupy the acceptor level, the distribution function for acceptor is given below. Thank you.
So moving on to other distribution function and comparison. The first is the Bose-Einstein distribution function applies to bosons. Bosons are particles with integer spin and include photons, phonons, and a large number of atoms. The Bose-Einstein distribution function is given by. So the next is the Maxwell-Boltzmann that applies to non-interacting particles which can be distinguished from each other. It also provides the probability of occupants for non-interacting particles at low densities. The Maxwell-Boltzmann distribution function is given by. A plot of the three distribution function is shown in the figure. All three functions are almost equal for large energies. The Fermi-Dirac distribution achieve a maximum of 100% for energies, which are a few kT below the Fermi energy, while the Bose-Einstein distribution diverges at the Fermi energy and has no validity for energies below the Fermi energy.
To derive this function, we need to start from a series of possible energies in which each energy have possible states and number of states, which can be written like this. Next, we use the Stirling approximation to eliminate the factorial signs. Next, we apply the total number of electrons in the system and the total energy, which are related to the number of states at energy and the probability of occupancy of each state. To obtain the maximum of the multiplicity function, we have to determine the A and B, and the derivation can be written like this. After that, we need to substitute the value of beta and EF, and we use the Lagrange equation and then compare the equation with thermodynamic identity. Finally, we get this equation, and that is how to derive the Fermi Dirac distribution function.
And that's all from us. Thank you for watching.